I've put together an uninterruptible power supply that uses a 3S2P battery pack. Before anything else, I'd like to demonstrate how this works and what this uninterruptible power supply has to offer. I've got 12 volts input here, and I'm going to plug it in. And now that it's on, I'm going to connect my Raspberry Pi and router to its output. I'm using a buck converter and a boost converter on the output. This one is set to 12 volts, which is what I need for the router, and this one is set to 5 volts for my Raspberry Pi. I've hooked up the 12 volt output to this guy and the 5 volt to this Type-C cable. I've plugged in the router and I'm going to turn it on now. This is what a reboot sequence of the router looks like. Keep this in mind because we're going to check if any of the devices restart when we disconnect the 12 volts input. This router takes a painful 2 to 3 minutes to fully start up, so I'm going to wait for that. In the meantime, let's hook up the Raspberry Pi. That's what the reboot sequence of the Raspberry Pi looks like. I've configured the LED to turn off once it's booted up. Oh gosh. I do not like that case. Alright, now I'm going to disconnect the DC input going into the UPS. If any of the devices restarts, you're going to end up noticing it. This LED is going to light up on the Raspberry Pi if it restarts, and for the router, every single LED will go out except for this one if it restarts. Let's see what happens. Nothing whatsoever. Now let's plug this back in. Absolutely nothing. Alright, with that out of the way, let's go over the design of this uninterruptible power supply and see how I made it. Let's talk about the battery pack first. Before I talk about how I made it, I'd like to go over best practices when it comes to handling lithium-ion cells and creating battery packs with them like this one. Ideally, for the cells you're going to use to create your battery pack, you'd want to use the same exact cells from the same manufacturer of the same capacity charged to the same exact voltage with the same birthday, same personality trait. You get what I'm trying to say. Your cells need to be as similar to each other as possible, and they need to be charged to exactly the same voltage before you connect them together in your battery pack. So once you have your cells, you're going to need these spacers to make sure that your batteries never touch each other directly in your battery pack, since that can be a safety hazard. The spacers will ensure that your cells never touch each other and always have a distance of 1 to 2 millimeters from each other. Once you have your spacers, you're gonna need a spot welder alongside a nickel strip that's adequately thick depending on the amount of current you're gonna be drawing from your cells. And you're gonna have to spot weld these nickel strips onto your batteries to connect them together depending on the configuration you're going with. For this UPS, I've decided to go with a 3S2P configuration, but you can of course change that around depending on your needs. Once you've appropriately spot welded your cells together, you now need to connect it to a proper BMS board that's going to monitor the voltage of each individual cell and make sure that all of them are always balanced. The BMS board you're using should also have the standard protection features of overcharge, overdischarge, overcurrent, and so on. With all that done, you're now going to be left with a battery pack that you can use for this UPS. That would be the best and safest way to put together a battery pack using lithium-ion cells. But at the same time, does this contraption I've put together work fine for this particular low-power application? Absolutely. So let me go over how I put this together. The biggest problem I ran into, which I imagine a lot of hobbyists can relate to, is that I don't have access to a spot welder. And so I use these holders to create the battery pack instead. These are the kind that are meant to be surface mounted on a PCB, and they work really well to create battery packs. To create parallel cells using these guys, I put solder on the top side of the pad on this holder, and on the bottom side of the pad on this holder right there. And once they're tinned, it's just a matter of placing them like so, adding a bunch more flux, and pressing them down with a soldering iron. The plastic does get in the way, but if you have a thin enough soldering tip, it will work just fine. You need to repeat this for the other side, and of course, since this is a parallel cell, you have to make sure that when you put the batteries in here, the negative of one cell connects to the negative of the other. And same for the positive. You can create a bunch of them as you like, and to connect them in series, you need to simply connect the positive of these two parallel cells to the negative of the other two parallel cells. Once you have that wired up here, that would turn this into a 2s2p battery pack with the negative terminals and the positive terminals located here. And that is exactly what I've done with this 3s2p battery pack. As you can probably tell by now, with this battery pack I have ticked a lot of boxes when it comes to bad practices with handling lithium-ion cells. I think using these holders to create the battery pack is fine as long as you're not going to be drawing a lot of power from your battery pack. In my case, I'm only going to be drawing a maximum of 40 watts from this battery pack, and so I think it's perfectly fine for me to be using these battery holders. However, the cells I'm using are not matched at all. They're all over the place, and the board I'm using here is not a real BMS, it's just a protection circuit that has short circuit protection, overcharge and over discharge protection. And even that doesn't work that well. The overcharge protection of this board triggers as soon as any one of these parallel cells reaches a voltage of 4.2 volts, which can prevent the others from being fully charged. It does state that it can do up to 20 amps, but I highly doubt that it would be able to do that without additional cooling with a heatsink and fan. And so if you are going to use this, I would highly recommend that you make sure that you never draw more than 10 amps from this board. And same goes for when you're charging it. Ideally, you'd want to charge your 18650 battery cells with a 1C charging rate, which means if your battery is 2600 milliamp hours, you should only charge it with a maximum current of 2.6 amps. Of course, that's going to depend on your specific cell. Some cells are going to be able to handle higher charge and discharge rates, but 1C is generally a safe bet if you do not know what your battery can handle. All of that is to say that if you're going to do this exact same setup, you're not supposed to draw too much power from the outputs, and you also have to use a current limited power supply on the input. For my specific battery pack here, a 12 volt 3 amp adapter is going to be safe for the input. So don't do as I've done here with the battery pack. In my opinion, the holder part is fine for low power applications, but you have to always make sure you're using identical cells, and if possible, avoid using a cheap protection board like this one and use a proper BMS. And of course, there's a possibility I might be wrong about something or missing some critical details. So make sure this video is not your only source of knowledge when it comes to safely handling these cells. With all of that out of the way, let's move on to the design of the UPS circuit itself. The original schematic for this UPS was put together by this person on Instructables. However, there were a lot of things that were wrong with the schematic they shared, and so I've put together my own version with a few improvements and modifications based on my specific needs. This circuit has two states. The first state is when you have the 12 volt DC input coming in from city power. It goes through this 1000 microfarad capacitor, which I don't think is really that necessary. The most important capacitors are the ones that are on the output, since they are responsible for storing some energy, allowing the MOSFET to switch between states without the outputs being disrupted. The input then makes its way into this XL6009 boost converter that is set to 13.5 volts, which connects directly to the battery pack's protection board. The reason this is set to a value over 12.6 volts is to make sure that the protection board has the ability to charge all of the cells beyond a shadow of a doubt. It is perfectly safe to provide this specific protection board with a slightly higher than 12.6 volt input, since even with a input voltage of 13.5 volts, it will never allow any of the cells to be charged over 4.2 volts. The input voltage from the boost converter is also going through this diode, which will prevent the power from the batteries from feeding back into the boost converter. And so this part of the circuit always ensures that the battery pack remains fully charged when you have city power. At the same time, before the 12 volt input goes into the boost converter, it makes its way to the gate of the MOSFET to instruct the MOSFET to not conduct from drain to source. And at the same time, it goes through this 1N5822 diode over to the output regulators. This diode up top here prevents the power coming from the batteries from being able to feed back into the input adapter. These regulators on the output can of course be changed around to whatever you like. In my case, I'm using a MP1584 buck converter for my 5 volt output. However, I do not recommend that you use this. I have noticed that this buck converter gets too hot to touch with a measly 700 milliamps of current draw on the output. And so if you're gonna use this, make sure that you have a heatsink handy. Ideally, I would recommend using a buck converter that has better heat dissipation and can handle high current loads. Of course, in the first state, the MOSFET is instructed to not conduct from drain to source. In the second state of the circuit, the 12 volt DC input is cut off, which immediately stops the batteries from being charged, and it also results in the MOSFET no longer being instructed to not conduct from drain to source. And so the battery power going into the source of the MOSFET is now able to make its way through the drain of the MOSFET into the output regulators. The drain of the MOSFET is connected through this diode to avoid the power coming from the 12 volts input from feeding back into the drain. The IRF 9540N switches really quickly, and along with the output capacitors, there is no disruptions at all. And of course, you also have to connect ground to the protection circuit, the output regulators, and to the gate of the MOSFET through a 10 kilo ohm resistor. I hope the schematic is understandable enough. I've made these bumps in the path when things are not meant to connect together. Of course, this is just the schematic that I'm using. You can change around a lot of stuff here, and there's still probably a lot of room for improvement. I put everything on a 7 cm by 9 cm prototype board, and this is how I've connected it on the back. And I haven't noticed any heating at all from the MOSFET, so the heatsink is probably overkill. Ideally, you'd want to design a PCB for this and get it printed and put all of the bare components onto the PCB to make things super compact, and that would make it easier to cram all of this into a enclosure. I'm fine with leaving it like this though. I'm going to plug in the input and let's measure some voltages. I have my multimeter set to voltage mode. On the input from the adapter, I have 12.4 volts. The output of the boost converter, responsible for keeping the batteries charged, is set to 13.5 volts. We see a slightly lower input on the protection board after the diode, and of course the voltages of all of the batteries look normal. On the input of the two regulators, we see 12.1 volts. On the output of this buck converter, I have about 5.1 volts. And on the output of this boost converter, I have about 12 volts. And also make sure that you verify all of the regulators you're using are set to the correct output voltage before you mount it to the circuit. So everything looks fine with the input DC voltage. Let's disconnect it now. And now on the input of the regulator, we get pretty much nothing. Same goes for the output, so the diode is doing its job. On the output of the BMS, I currently have 12.28 volts. And of course, the output of the output regulators stays exactly the same. And some of you might be thinking, I don't have any switch for the input power coming from the battery pack. So what do I do if I want to disconnect the battery power from the UPS for whatever reason? Well, for that reason, I have implemented a touch-activated power-off switch on this cheap protection board. To power it off, you have to touch right here. I'm just kidding, of course. This specific protection board gets triggered when you touch around on it with a sweaty finger, which causes it to shut off the output until you provide it with a charging voltage on the input, which can be used as a power-off switch. Or add a switch that can handle the amount of current you're going to be putting through it. It's really up to you. See you in the next one.